board. If there were no friction between the boy's feet and the snowboard, which way would the boy go?
You said there's no friction?
If there's no friction, if the snowboard had no friction between it and the feet,
I'd go to the right,
yeah, the boy would go to the right. Therefore, which way is friction acting on the boy?
to the left.
Oh, oops. I meant to do an S there, and an S here. And then B for boy. And now we have dad and ground. Which way is the friction acting on the dad?
Does the weight of the boy matter? Does the weight of the son matter?
No.
No, okay.
To the right,
Why to the right?
that's where he's accelerating.
Isn't he moving to the right?
So friction would be moving to the
Oh, that's what I was saying, was he's moving to the right.
He's moving to the right, yes. So you're saying friction is actually to the left?
Yeah.
And you agree? Anyone wanna, is that a head shaking no?
I just, what you did on the last problem, that way.
And this is a tricky one, because the dad is moving to the right, he's accelerating to the right, and you're thinking, well, friction opposes that. The trouble here is, what part of the dad is actually touching the ground?
His feet,
Foot, singular.
1 foot.
If it were frictionless, which way would his foot go? His foot would go to the right?
But if the boy's on that end, he'd be going to the left.
If what?
If the child's on that side, would he be pulling to the left because it's frictionless?
Um,
Or you said the weight of the boy doesn't matter, so.
yeah.
Yeah.
So if he is walking, and while I still can, okay, this will be, see, dad's going that way. It just takes me longer than it used to. All right. So if I'm walking in that direction, think I've got my foot on the paper. As I walk, which way is the paper? So, therefore, the reason the paper went that way was because of friction. So if I push with friction that way on the paper, which way is the paper pushing on me? So, it's not the way the dad is moving, it's the way the foot is moving. He's basically pulling his foot that way, dragging on the ground. That's the friction from the dad there, and friction from the dad there. Now, there's another way of looking at this. If they are accelerating to the right, there has to be some force to the right. We have not gotten to this yet, but the total force acting on an object, the total force is equal to the mass of the object times the acceleration. This is what I consider the most important equation in all of physics. This is chapter 4. But I have only two vectors in it, force and acceleration. They have to be in the same direction. Since they are accelerating to the right, the net force has to be to the right. At this point, there are no forces acting on the dad to the right. So if he's accelerating to the right, there's got to be something accelerating him that way, and it's the friction. If you're not convinced that the friction can propel someone forward, well, we just had a week of ice out there. If you tried walking on ice I think you realize that you need the friction in order to actually move quickly. Same over here with the sled. If that friction were not there, there's no force acting on the sled to the right. That's the force that propels, that accelerates it to the right. Over here, it's the tension accelerating him to the right, because part of the tension is in that direction. Here, it's that friction that's accelerating him to the right. This friction right here, that's what's causing the snow to get kicked up in his son's face. Or if you were in a car, it's going to be that friction acting backwards, which causes mud to get shot out the back if you're stuck. Yeah, you've got it. If you're stuck in bed, don't gun it. Questions? Because there is no other in this problem, there should be an even number of forces. Matter of fact, there should be an even number of weights, an even number of normal forces, even number of tensions, even number of frictions. There's not necessarily an even number of forces acting on any one object. So that's got four, that has 5 acting on it, 2, and that's fine, just so long as I have an even number of normals, even number of frictions, even number of tensions, and so on.
Wait, tension's not even.
Pardon?
Tension's not even?
It should be an even number of tensions. I traded off at the end and
Oh,
just threw in the catch-all, etc. We have 4 tensions, we're good there.
okay.
If other gets thrown into it, then you could have an odd number. So,
But there's 6 frictions.
pardon?
6 frictions,
Yep, okay.
but 4 tensions.
Yeah, they don't have to be the same even number,
Oh.
even as in not odd.
Oh, gotcha, okay.
All right, let's take 5. Come back and try to connect some of this with other things. Wrap up chapter 2. And we get all dance. Have a dance of joy inside. Questions? Let's talk about inertia. Inertia is a property of an object which is very much related to our mass. The greater mass an object has, the greater its inertia. It's a tendency of an object to just want to keep doing whatever it's doing. Hewitt, in the last several editions of the book, related inertia to laziness. If you've read the commentary, you know my feeling on that. If you haven't read the commentary, no. Inertia is not laziness. Stubbornness, I might have agreed with. Laziness, no. If I'm digging a ditch, if I'm lazy, I want to stop digging the ditch as soon as possible. If I'm stubborn, once I start digging the ditch, I don't want to stop. I'm going to keep doing whatever I'm doing. Inertia is related to once it starts, it doesn't want to stop. Now, inertia is also, it doesn't want to start if it's not hadn't started already. But it wants to keep doing whatever it's doing. My daughter, who's now 26. That's just shocking to think of, and married. It's even more shocking. Not because of her, just because I'm that old. My daughter, when she was little, my wife and I called her Inertia Girl. If we needed to go to the store, she'd be too young to just leave in the house with the dogs. And so we'd take her with us. Well, she was in the middle of playing something, she didn't want to stop, she didn't want to go to the store. But we'd get her into the car, we'd get to the store, we'd park, she didn't want to get out of the car. We'd get into the store and do our shopping, and it was time to leave, she didn't want to leave. She'd get to the car and get home, she didn't want to get out of the car. Whatever she was doing, she wanted to keep doing. That is why we called her Inertia Girl. And by the way, I do have her permission to tell the story. I won't get her permission for all the stories I might tell to my kids, but that one I do. So, inertia deals with wanting to keep doing whatever you're doing. Now, in terms of physics, that is a little bit more specific. It wants to keep at a constant speed in a constant direction. So it wants to stay at constant speed, and that speed could be 0. Constant speed in a constant direction. Now, as we'll get to in chapter 3, if you're traveling at a constant speed in a constant direction, you have a constant velocity. And a v with a vector symbol over it is the symbol for velocity. So Newton came up with 3 laws of motion, one of which, the first law is just that objects have inertia. Sometimes referred to as the law of inertia. The more common wording is an object at rest wants to stay at rest, an object in motion wants to stay in motion. And yes, an object in motion wants to stay in motion, but an object in motion wants to stay in motion at the same speed, in the same direction. Now, if you want to change the speed or the direction, you have to apply a force. And so that's when the forces come into it. Chapters 2 and 3, physicists would love to teach them both simultaneously, which you can't do. You have to teach one, then the other. Most textbooks will do the motion stuff first, what's chapter 3 in Hewitt's book, and then do forces. Hewitt does it the other way around. I'm still a mixed bag about which way I prefer. There are advantages to both. But if we want to change this, if we want to change the velocity of an object, we have to have a net force. When I say net force, I mean a total force that is not 0. Now, as we talked about before, force, it is a vector term. Got the vector symbol. Tell me that is a vector, and F for force. As a matter of fact, that force is related to mass times acceleration. Chapter 4 will go into a little bit more detail on this one, but this is the second law. First law is that objects have inertia. Newton's second law is this. Actually, he wrote it a little bit differently. Well, one, he wrote it in Latin. He wrote it as acceleration is force divided by mass, as opposed to force is mass times acceleration. Mathematically, they're the same. This is one of those things that I generally write it this way instead of this way. But it's a matter of force causes acceleration as opposed to acceleration causing force. It's a dependent, independent issue. So then, introduce the term equilibrium. Equilibrium. Chapter 2 is about equilibrium for the most part. Equilibrium is related to that if an object is maintaining its velocity, in other words, constant speed in constant direction, it is in equilibrium. So equilibrium actually has 3 different meanings here. It could mean that the change in velocity is 0. There's no change. Your velocity is constant. Now I put the vector symbol over the 0. This is known as a 0 vector, and it just indicates it has a magnitude of 0 in the direction of whatever you want it to be. It's a mathematical thing. I got a vector on the left-hand side, I need a vector on the right-hand side. So if object's in equilibrium, the velocity doesn't change. I am not claiming that the velocity is 0. All I'm doing is claiming that the velocity is not changing. If the velocity is not changing, as we'll explore later on, the acceleration is 0. Acceleration deals with the change in velocity. And if you look at the equation I wrote over here, if acceleration is 0, then the total force is 0. The net force or total force, whichever way you want to do it, is 0 newtons.
So the first one you wrote is the velocity is not changing, and then the second one is since there's no velocity, there's no acceleration, and then that means that there's
Since
no
velocity is not changing, there's no acceleration.
Okay, and that means that there's no force.
The total force. The total force is 0. There could still be forces, but they would balance each other out.
Okay.
And pro tip here on a test, if you see the word that the object is in equilibrium in a test problem, then immediately, once you see it's in equilibrium, all three of those are true. If any one of those is true, the other two are also true. Because I've given problems where I had an object in equilibrium, asked a bunch of questions. The last question is, what's the acceleration of the object? Well, it's in equilibrium, acceleration is 0. This is the concentration of chapter 2. Chapter 3 will bring this stuff into it. Chapter 4 will go into more detail on that. Chapter 5 we've actually already done when I talked about the forces coming in pairs. That whole bit about forces in pairs, each force in that pair acts on a different object, same magnitude, opposite directions. That's the third law. We'll do that in more detail in chapter 5. All right, so let's apply this. Questions before we apply it? I have a beam in equilibrium. Let's say it's a 50 Newton weight. The tension in this rope is 30 newtons, the tension in this rope is unknown. What is the tension in the unknown rope? Now, some of you probably have, I'm guessing, an intuitive feel for what the unknown is. Just blurt it out.
20 newtons.
There we go.
Sorry.
Yep, 20 newtons. Total force is up equal to total force is down. Once I establish this in equilibrium, that tells me the total force is 0. So whatever I have up, what I have going down. I'm going to work it out the same, I'm going to come up with the same problem, or I'm going to solve the same problem, except I'm going to throw in some more letters into it. Potentially it's going to make it look more confusing, I'm hoping not, but for some of you, this other way might click better. I'm just going to label that as X. It's an unknown. I'm going to establish a positive direction. I can make up positive or I can make down positive, it doesn't matter, I'm just going to pick one. I'm going to make up positive, so I have 30 plus X plus, well, 50 is going down, so that's not mine, plus negative 50 equals 0, because I know the total force has to be 0, and this is the problem we're solving. If I combine those two, I have X minus 20 is equal to 0, and then solving for X is equal to 20, and then tack on the units at the end. Please don't forget units. For some reason, I worked my way up instead of working my way down. But this is the same problem, just solved, making it look more math-like. How fast is the beam going?
It's not, it's an equilibrium, so no velocity. Or acceleration,
There's no acceleration.
no acceleration.
What does that tell you about the velocity? How fast is it moving? I'm hoping from the silence that that's your answer.
0. Oh,
I didn't give you, there's not enough information. This could be moving or maybe it's not. Right now, picture yourself that you are still. Even if you're wiggling around a little bit, just pretend that you are in equilibrium at the moment. From my point of view, you're still. As I walk towards you, you are no longer still from my point of view. That doesn't change the fact that you're still in equilibrium. My movement does not change your equilibrium status. How fast an object moves depends upon who's observing. So, is it at rest or is it not? Well, it depends upon the observer. Typically, we say an object moves if it moves relative to the Earth's surface. It doesn't have to be. So, how fast an object is moving has nothing to do with whether it's in equilibrium or not. It does, however, adding another vocab word into it. If the velocity is 0, so here it's change in velocity. If you see the delta, that means change. This is a delta, and it means change. If it's an equilibrium and the velocity is 0, this is known as static equilibrium. If it's an equilibrium and the velocity is not 0, then this is dynamic equilibrium.